there is a difference between a sound level analysis and if you listen to the sound, your impression by hearing it. Why is it that? This is a crucial element. Every acoustic engineer needs to understand why there could be a difference between the analysis result and the sound impression, depending on which analysis you're choosing and depending on how you listen to your results. I will explain this here step by step. Stay tuned. To get this right, we need to start back in the days of mankind. In the beginning, we only listened to sound and they were related just with our ears. But when we built machines, it was obvious sometimes it can be too loud. There was a demand, we need a limit. We have to measure it and get a number and say, okay, this is too much. We have to below the limit. So this was the beginning of measurement of acoustics. So how to measure? Well, we can measure the sound pressure, but not the total pressure. It's the deviation of sound pressure. That is sound. So if we measure it, it looks like that. So it's a fast changing value. So where is a number in that signal? Okay. So the first idea was, okay, it's a changing, alternating current. So let's do the same like we did it for electricity. Mr. Tesla explained to us here, we have a sinus sweep and the energy in this sweep is the effective, the root mean square value. So square root of 2 gives us the energy in a wave. Okay, so we can use this also for acoustic measurement and get a value. But in acoustics, we have the problem that we have an extremely wide range of measurement result. Could be very small values, but extremely high values by doing this. Okay, there was the point of Mr. Bell. Here's the idea, okay, it's not a problem. What we need is a reference point. We defined it as P0, okay? This is 2 by the power of minus 5. Exactly 2? Yeah, 2, it's easy to calculate and hey, it's just a reference. Okay, all right then. And if we make a 10th logarithm of it, then we get a really small number. And that's what we call Bell. That's my name. Okay, so we do this and we get, well, then we get really small numbers. We get just a number up to 10 or 11. It's not a good scaling if you want to really precisely work on that. Not a problem, then we multiply this value by 10 and then it's not a bell, then it's a decibel. And so we got decibels now as an acoustic unit. Fine. So we built a machine and tried it out. Does it work? I was not there at that time, but actually it was really clear that it does not work properly. Sometimes we have a really low, loud noise and it gives a value of 60 decibels. And then you have a really high frequency noise that gives you maybe 40 decibel, but it's much higher. Your machine is broken, it doesn't work. You have different frequency in your signal. It's not like electricity, you have high and lower frequency at the same signal. Then, okay, we have to check this. Okay, it seems like humans have different evaluation, different perception of depending on the frequency. So we make a listening test. And that's what they did. Fletcher and Manson make a hearing test, giving you a sinus tone, really soft, 40 decibel. And you can adapt another tone with another frequency as long as it has the same appearance, the same loudness. Okay. And by doing this in some steps, you see, okay, at low frequency, it seems like we didn't hear that much. So we can drop this. And high frequency either, we don't hear that good. Yeah, or we are more focused on the 1 to 2 kilohertz. Okay, so we build a line to adapt this. And this is called now dBA, estimated 1933. Our first metric to evaluate acoustic measurement as human hear. So what's up next? So 1940, nothing. 1950, nothing. 1960, nothing. dBA rules the world. It's incredible. But there was some criticism. If you make the same evaluation for higher levels, so 50 or 60 decibel, and make that a comparison of louder sinus tones, you get another result. So you're dropping at lower frequency and the dropping of higher frequency isn't that much. It's going more for a flat line. So our ear works more flat on higher levels. So that's why there is a dBB or dBC weighting depending on the total level. But you recognize this effect when you listen to music. If it's good music, you turn up the volume, then it sounds good, then you feel it, and you like to dance to it. Because then you listen at the level the music is supposed to be heard. But if you turn down the volume, not all frequency goes down linearly, no. Then you change from C weighting to an A weighting. That means it's like your ear going to the equalizer and takes down all the low frequency dramatically, minus 20 decibel, and also the high frequency you're just taken out of the signal. And you're just a pure middle tone stays. You recognize still it's the same song, but there is no motion in it. It's so empty. It's without any dynamic. Okay? Good amplifiers have these loudness options. So when you turn down the volume, artificially the low and the high frequency are lifted up again to compensate this effect of human hearing, just to stay at the same experience of the sound. So the message is, if you want to evaluate the sound by listening to it, you have to make sure that you listen to it at the original level. Otherwise you hear something different, a different frequency weighting. You're not allowed to do this. Well, the acoustic engineers in those days might say, I just want to have a number. I always take A weighting, it's fine and it gives me the lowest level, it's cool. So dBA still rules the world. Until 1974, Eberhard Zwicker made a really good point. He said, hey, hold on. To create this weighting, you only compare sinus tones, but my machine that I want to evaluate doesn't create a sinus tone. It's more a really complex combination of frequency, broadband. Does it also work on broadbanded noise? What does happen if I hear two tones, two frequencies at the same time, with other two frequencies at the same time? Let's check this. And he found out humans have a masking effect. We've seen this drawing. It means that you don't hear all the frequency, you only are blocked by frequency, and the evaluation of the loudness of other frequency depends on what is aside of these frequencies. It's really complex. I think it's easier to understand this effect if I give you a picture. This is your tone. You're from left to right, there's something change over time, and low and high frequency coming from bottom to the top. And now I'm asking you just to see how big is the level of plate A, yeah, in this moment, and this frequency, in comparison to point B, the level, I mean how bright it is. And obviously point B has more light, has a higher level. Hold on, there is a masking effect. There's a big disturbance that gives a shadow over B. That means for human, you're not able to compare A and B objectively because you are disturbed by the surrounding. Let's make an object change. I just move B out of the shadow. Just copy paste this part and move it out. And you see, in reality, it's much darker. I didn't change the color or the limit, yeah? Just move it back slowly, just watch the B. I move it slowly back in the shadow, back in its place. And as you see, if it's coming to it, you see it has still the same brightness, the same level. And if I'm going up now to A, out of the shadow, you see B and A has exactly the same limit. Let's move it down again. B goes back in place, there is no change. It just feels like that B is brighter than A. So this is a crucial point. Humans evaluate sound level always depending on the surrounding. And the same goes for acoustic evaluation. It's the same brain, it's the same processing algorithm, okay? I still don't believe it. Let's move A down. A is exactly the same as B. Of course, this is a shock to any acoustic engineer. A dBA does not cover this essential effect of humans. It feels like you've been to a doctor and you have really, it was an unpleasant visit. Well, Mr. Pamphus, I look at your blood values and I say, you drink definitely too much alcohol. You can't drink every evening a beer. You have to stop this. And by the way, you can't eat meat every day. I mean, probably he's right, but you don't like to hear that. You have to make a big change in your life. You have to do everything different than you've done it before. Nobody likes to hear that. So there are two options now how to react on this message. First, you accept it. Then from now on, I will try to eat less meat. I get used to it and don't miss the flesh taste anymore. And of course, yeah, I can't just drink maybe only on Saturdays. I will do this in a way, yeah. If it's good, then maybe why not? One option. Or second option, and this is the common option. Most people do it this way. I should change everything I've done it so far. No, I never go to this doctor again. So the most people stay on dBA analysis. The question of course remains is, but who's changing to psychoacoustic analysis? Well, it's a clear answer. I can give this to you. is the new companies, the new areas. For example, PC fans. The people who want to evaluate PC fans, they see as, okay, maybe this has a higher coolant effect, but this is definitely too loud. Well, this is so good, I can't even hear that. No? And these two are quite close to each other. This is slightly a bit smaller, it's a bit bigger, and this is just in the middle of the very bad one, the middle one. Is an analysis that gives us this evaluation back as a number. And they tried it out. Of course, dBA, not the right order. dBd, dBc, But what's this? That's exactly what we need. This is the best one, definitely. Really low number, and this is a very high value. These tones are very close together, which is a little bit better, and this is just in the middle with 3. That's exactly what we hear is now as a number. Write down its zone. And since then, people measured in zone the level of PC fans. Heat pump is also a new industry. Of course, they measure the sound power from that device, but more important is that the neighbor is not disturbed by this machine. There's a noise in there, it's a tone, it's really small and has a fluctuation in it. You say, oh, I can't stand it, it has to move out. And the dBA level doesn't give you that feedback. Drones, what a bad noise. They are not loud. You only hear them if they're really close to you, but then suddenly you say, wee, it's so bad. Because they have almost the same frequency, really close together with 4 propellers, it creates roughness. It's an effect. And they have tones in there. Very important effect. So you want a value for that? Go for these questions. If you have a constant noise, woo, it's an average value, it doesn't change. But if there's small deviation in the tone or in the frequency, people will hear that and say, well, that is so bad. The total level, the average, is actually the same. But people say no. The reason for that is that humans have a very high temporal resolution of sound. I will explain this back to my image, okay? So what is the temporal resolution of a normal fast Fourier transformation? If this is our noise, the first thing a Fourier transformation does is we create a block length. And in this block, we make an average value for the frequencies in there. So if we look at this first line, we see there's a bright, a dark, and a bright square. So in average, it's quite a light gray value for this frequency, okay? And then we do, for the next time lapse, another block, a little bit overlap. And it's a bright, dark, bright. It gives also the same brightness again. So in the average, we see there is no change in the signal at all. Okay, obviously we have a too slow time resolution. Okay, we need a higher time resolution, and of course we can change this in the fast Fourier transformation. We just take a smaller block. So we use this now. So we take a smaller block now, maybe just concentrate on one block, so we have high time resolution, but now we lost the frequency resolution. We always have to take 3, I will show you later on why I take 3. So we have white, black and white. This gives us again a quite bright average for this broader frequency range. Then with some overlap, we do a next. This is bright, 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 and black, black, black. So it's a little bit darker. And then another block gives you black, black, and white. So this is the lowest one. So this analysis tells you slightly the level drops. You miss something. And that's the point when you start to make changes in the block size, in the analysis, maybe in the sampling rate, to get a better resolution. Let's see how the math is behind. If we want to have a high time resolution, it's calculated by the block, so I have to choose in the analysis, divided by the sampling rate of the recording. While the frequency resolution is just the sampling rate of the recording divided by the chosen block size in the analysis. If you want both, it fits. So if the total resolution of your acoustic analysis, so delta F multiplied with delta T, is always 1. Exactly 1. You can't have more. And it doesn't feel good. It feels like there should be better. And that's why you're trying around. But why are you thinking that should be a little bit better? Why are you disappointed with the result? Simple explanation. If you make this calculation for humans, so the frequency resolution, time resolution of a human perception, we get a value of 0.3. Humans can evaluate sound with a 3 times higher resolution than a Fourier transformation. Not 30%, 3 times higher. How can this be? We have so much high-tech computers and they can't be working better than my grown ear. They are analysis which delivers higher resolution on acoustics than the Fourier transformation. For example, the HSA, I'll give you a video on that. If you calculate here, you get a resolution of 0.0625. This is much, much better than a human can hear. If you use that analysis and look in the time, you need to slow down the playback because you can't hear that fast as this analysis have a time resolution, okay? So this goes for the HSA. But if you choose a Fourier transformation with the idea of block averaging, you always get a resolution of 1. Always. If you're thinking about using a more sensitive sensor or a bigger range, or maybe higher sampling rate, different block size, even a better computer. Nothing will change the resolution. This is a property of a Fourier transformation, okay? So what is the trick of the evolution? Why is it possible to be 3 times better than a Fourier transformation? If the noise hits our eardrum, it's first amplified and then sent into the cochlea, this spiral thing. And this is a brilliant analog filter. It divides the time signal into low, middle, different frequency bands. Okay, would look like this. So we have up to 24 different frequency bands, and for each frequency band there are hair cells located on these cochlea, and they listen to the time signal in their frequency band. And that's why we still have the full time patterns available, separated now in frequencies. And the great thing is, at this point, we didn't done any averaging, no overlapping, no hanging, pure time signals separated by frequency. And that's the crucial difference. We listen to time signals. We do not average. No human does ever do an average analysis. Oh, I've been to the concert yesterday. Oh, tell me, how was it? So an average was 92 decibels. Wow, it sounds good. No, we don't evaluate sound by averaging over a certain time block. And that's why, of course, there is a difference in block analysis and listen, okay? The main advantage is that in all these frequency bands, we hear any amplitude modulation. We can hear that really precisely. And we get analysis for each frequency band. And the crazy thing is that each analysis gives now a feedback to the brain what's happening in there. Maybe the lowest frequency say, wow, here's some random noise, not a big deal here. The next frequency, here's some nothing in there. And then third band say, admit we have high, low, big changes. And everyone say, whoa, listen to that, all eyes on you. So depending what's happening in the frequency band close by, we listen or don't listen to what's in that frequency band. So this is a very important fact. And we can use that. For example, if you want to wake up someone, you can scream as loud as you can so you start up. Or if you don't have so much power, only have a battery device, 0.5 volts, yeah? What do? You just send a really short amplitude modulated sinus tone that just hit one bar and making and you wake up, alert, all eyes on you. It's not that loud, but it's just pointing out at using this effect of human evaluation of sound. But where is the disadvantage of this system? If there are 2 frequencies in one band, obviously we only hear one signal. So one is masked and the other is now alternating its level by the other frequency. So if this is a really small gap of 2 Hertz, we will hear woo, 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 and this sounds not good. We call this fluctuation. Or another effect would be if there's 70 Hertz between these 2 frequencies, alternation would be sound like bad noise, broken. No, you have to avoid this effect. That's what we call roughness. The funny thing is, if you look at devices that only built to create sound, music instruments, a guitar for example. So first your first string you can create a tone, and there will be one tone in one of the bands, okay? And it doesn't make sense to create a second tone in the same band. We would not hear that. It only makes sense to go, you have this distance, and this width of these bands is about a 3rd octave. That's why a 3rd octave analysis is so common. If you look at an FFT frequency analysis, it only has the same frequency resolution. At high frequencies, only a carpet of frequency. What's the value, yeah? So it makes sense to sum up this to one value in frequencies, and 3rd octave is quite close to the real here. At low frequency it doesn't match at all, but that's the best we can have. That's why it's so common. So what the guitar does is, You go 1/3 octave higher from E to A, and then I can hear this second tone. That makes sense to get a second string 1/3 octave higher. So if I have a C, then it makes only sense to create 1/3 octave higher C, D, E, and non-band Y, E, F, G, and then I have an accord, G, E, G, sounds good. And we have 3 bandwidths close to each other, hear the same level and say, I hear a good tone, I hear a good tone, you too? That sounds good. Well, if this effect is so crucial, then maybe I should use this also in my acoustic analysis of machines. How can I do this? Very easy. There are analyses that do exactly that. They are called psychoacoustic analysis. They deliver exactly values for all these effects I just mentioned. There's loudness, how loud does something appear, depending on the frequency surrounding in the front, the background, loudness. There's roughness, this is bad noise, just the analysis gives you the value. Fluctuation change, how bad this noise is in your noise, in spite of any averaging, then you wouldn't see that effect. Or you're looking at tonality. If there's one tone that picks out, obviously everyone will take the focus on it. This effect is given a value. And there's sharpness. It's a relation of high and low frequency in the same noise. So in this picture, if you have a lot of high frequency in there would be too much weight on the board and will turn over. So if you add some low frequency here, it will come back to scale. It will be louder, of course, because you added one, but it will be fine noise and it's equalized and it sounds good again. That's the sharpness. Okay, I got this point now. But hey, I'm used to use dBA, 3rd octave spectrum, FFT analysis. How can I make use of these psychoacoustic analysis? I mean, is this a conflict? Not at all. In the next video, I show you in really detail how to make use of these brilliant different analysis on your normal analysis work task. You will love that.